now continuing with the neural implementation of the free energy principle idea. And the first thing in this regard is that the assumption is that the brain actually performs a gradient ascent on the variational free energy. And to this end, what we need again is the idea of gradient ascent. So remember, so we are talking about, of course, learning or updating the variational parameter. So what we are interested in is a sequence of variational parameter estimates that is generated by some algorithm. So something happening over time, over iteration steps. And in most fundamental terms, this is supposed to work in terms of gradient ascent. So as we saw last time, after some initialization, the basic thing of a gradient ascent scheme is that you take the current parameter, estimate, and you add to it the gradient of the target function or objective function, in this case the variational free energy, at the current parameter setting, and this is your updated parameter. To do that, one needs to evaluate the gradient, so one needs the gradient of the variational free energy function. That depends a little bit on which terms one include or not. So I will not be very precise about this at this point, because also the actual algorithm that is used by, or that is sometimes discussed with respect to variational inference, is a little bit different from this basic gradient ascent algorithm. Then my personal view is that something like a globalized Newton with Hessian modification is a better algorithm. So there's a zoo of algorithms. The most important thing is that you have these iterative parameter updates. So that's kind of the bottom line here, iterative parameter updates. So that you start with some initial value, which might be your prior expectation parameter, and then you use the gradient of the variational free energy to adjust this parameter. This is where I actually want to keep this, because otherwise we would have to go much more into details about nonlinear optimization, which we don't want to do right now. So the idea is, again, that you have an initial parameter setting, and then you iteratively update that. By these iterative updates, maximize the variation for energy, which renders your variational distribution a better approximation to the posterior, and your elbow of free energy approximation of the log marginal likelihood. So what's the idea with neurons now? Well, the idea is you take certain parts of this algorithm and you overlay it on a figure where in the background you have something that looks like something neural, and then you have das habe ich von Ihnen ferngehalten. Oh, interesting. Then you have something that looks like a neural theory. So let's go over this. So here's the external world, and now some causes some activation, and we don't talk about the first neural representation now. Because this obviously shows some cortex, we now talk about something like V1, where the data is represented. So think of V1 as just basically the same activation pattern as in the retina, which is of course not the case, but otherwise this would be the retina, and it doesn't look like the retina. So the idea is that there is some representation, and the idea is that this is in deeper pyramidal cell layers, because what is represented in the external pyramidal cell layers, which is actually where you can record the EEG from, is the difference between the data representation and the model prediction. So where does this model prediction come from? Well, it comes from a higher level. So the idea is that in this case, an intermediate level projects the current estimate of the variation expectation parameter to a lower level. This lower level in the external pyramidal cell layer represents the prediction error. So in general, this idea about neurons representing prediction errors is not bad, because that means if there's no prediction error, so if everything is as expected, so if nothing changes, you don't need neural firing. Only if something changes, you fire, because if something changes, there's a prediction error. And this is kind of metabolically, this is meaningful. It's also, it's fairly ubiquitous in neural recordings. So whenever something changes, you see some change in activity. If things then stay similar, then activity wanes or adapts or habituates, however you want to call it. So this general idea that neural activity measures some mismatch or prediction error is a good idea. Whether it's exactly this prediction error here is, of course, postulated by the free energy principle. The idea is, that here you have this cause represented. This is projected to a lower level in terms of the prediction, so it's mapped through this nonlinearity. And then the idea is, and don't ask me how this is supposed to be, but the idea is that this lower level sends up a gradient component to a higher level. At this intermediate level, there is a representation of this expectation parameter, and in a deeper pyramidal cell layer and in an external pyramidal cell layer, or at a high, something that you can detect again, there's again a prediction error, in this case between the cause representation, so the variation expectation parameter, and the prior expectation. And then at the highest level, there is the representation of the prior. So the idea is that always external pyramidal cell layers represent prediction errors. Deeper pyramidal cell layers represent the representations of what is what is being represented, and then, and I didn't say that clearly, the prediction error is actually together with the gradient fed backward to change the representation. And this happens here, and it doesn't really happen here because this prior is not updated. But this is the general idea. Now, of course, there are many questions and there are no answers. So if you want more details, you have to study that. So you have to do a research project on that. Because there are just not more answers. I mean, there might be in this or that paper that looked a little more in detail into that, but in general, there are actually not more answers. So if you now want to really link this, for example, with EEG recordings, because you can measure, or you believe that you can measure prediction errors, or you want to link this with invasive data, that's a research project, and you would have to first see what is out there, and you will find that it's usually then when it comes to details, it's fairly vague, and then you have to come up with your own interpretation of this whole thing and make it more concrete. Yeah? So I cannot really say anything more about these ideas. But that's the general idea, that these terms that you have in the elbow, that they map, the prediction errors map onto external pyramidal cell layers, and of course also the actual things need to be represented, and this is in deeper layers. One can say a little bit more, though, about examples and study this in example settings, and this is what I want to do now. Are there any questions about this that are more on the conceptual level and not how exactly this works? So if you're interested in this, do a master thesis on this and a PhD and the rest of your research life. Where do I want to go? So what I then want to discuss for the remainder is a little example of this that I programmed, and to make this concrete. Oops. No. So, but we need to go back here first anyway. So to have an example of this whole thing in terms of our little model, I came up with the following example, inspired by my cats. Because if you have a cat, you might have noticed if there's a blanket and there's something moving under that blanket, they go crazy. And this means to me that they can infer that there is something under the blanket. So they have a representation somewhere in the brain that there's something going on beneath the blanket. So they have a model that tells them there's something going on, although they don't see it. So they can represent some latent variable. So what I basically wanted to model here was tracking something moving under a blanket. And what I show now here is basically tracking something that is static at a given point. So I have the moving thing as well, but this involves Kalman filtering. So I'm not discussing this right now. It actually involves extended Kalman filtering, so non-linear Kalman filters, if this is over time. So here I'm just basically discussing the case that there's basically something static under a blanket. And this is the way I model this in the Frame principle for perception setting is that there is a latent variable x which is a two-dimensional vector which represents the 2D coordinates of this object that is being tracked. So the idea is there is if you want, a mouse under a blanket, and this is located at a certain location in 2D space, which is this 2D coordinate. And the cat, in this case, has a prior representation of where this might be, and encodes this as uncertainty over the latent variable x. So we have this prior setting px and x mu x And how do I do it? Yep. Lambda x minus 1 I2. Yeah. So essentially, this what this is supposed to mean is that the cat has a prior expectation that there is at some location something under the blanket. Of course, the question is how tight this prior is. So you can have a very broad prior, basically assigning probability density to the entire blanket world, or you can have a what is it, type prior? You can have a very loose prior, so you have a broad prior where you have basically uniformly distributed probability density, or you can have a tight prior that you think always there is something. But of course, it's more interesting if it's a little bit broad, so if you have kind of a uniform prior going to objective Bayesian realms almost. And then the thing is that this coordinate is mapped onto the observation pattern in the retina or V1, and this mapping is done by this function f, which here basically serves as this blanket. So you don't see the coordinates, but what you see is the outcome of this object being there if it's under a blanket. And this I represent by this exponential bump. So essentially what you get here is a large d square dimensional array, which you can think of all the values, the height values of a blanket represented in the world, but then also in your retina, or in the cat's retina, which is, of course, governed by the true but unknown location or the state of the random variable. Yeah. So one thing is, so you have to think about this a little bit mathematically or computationally. One thing is you have a 2D vector that says at 1, 1 there is a bump. The other thing is you have a large array of numbers representing the height of everything of a blanket, where some values are a little bit larger with some extension sigma, and the whole thing actually is d squared, where d is the discretization of this space. So this is essentially, so I think it's a little bit easier if I show you a picture of this, and then it should be a little bit clearer. Question is which one this is. This is actually the wrong one. That's the right one. So this is again, so this is the story here. There is in 2D, there is a real external thing, which are these location of this external objects here, this red number. So this here, and then the agent, so the cat has a prior, which is just centered on 0, and in this case has a fairly, it's fairly tight, but it's not too tight. And this is the true but unknown cause. So this 2D vector, and what is actually observed is something like this. So this sheet of data where, of course, in addition to this function f here, there will be this observation noise, which is, of course, again, Gaussian distributed, and is a multivariate high-dimensional Gaussian, because this is ID squared. And so here you see then it's getting a little bit slow, maybe because I have too many things open. Here you see the bump, roughly at 1,1, and here you see some noise. So the important thing is that there's also, of course, noise on the representation. So you have a blanket which is not completely nicely and completely flach, but there are some bumps everywhere, and one bump is higher. And based on this model, I then implemented the variational free energy. So essentially what this model is about is, of course, this definition of what is x and what is the function f. And this is what I've shown you. And then the model is complete. And now I told you a little bit of a story about what this is supposed to be, but the model is complete, and one can just apply the variational inference framework, the fixed form variational inference framework. And one thing then, of course, one can evaluate is the variational free energy, or the elbow. So this is the negative variational free energy function, meaning we want to minimize this. Thing is, in nonlinear optimization, one always wants to minimize things. In maximum likelihood or variational inference, we of course want to maximize something, but we can also do maximization by just minimizing the negative version, and this is what is done here. It's just more in line with nonlinear optimization, hence minimization. And this shows what's going on if one uses a little bit more advanced gradient ascent algorithm. So the initial expectation parameter, variational expectation parameter, is set to the prior one, and then there is these iterations of the algorithms that I told you about are happening, and what is shown here are the prediction errors. And with this globalized Newton method, one jumps around a little bit, but slowly enters the well. And what happens here is that the squared prediction errors, so our epsilon, should be epsilon, not e, epsilon at the lower level are minimized. Actually, at the higher level, they get a little bit larger. This is a little bit easier to see if one uses this temporal local linearization method that is used, for example, in DCM. So here things are a little bit smoother. So here, essentially, the variational expectation parameter, which is of course a 2D thing because it wants to estimate this 2D vector, enters the well. The prediction errors go down. Interestingly, the prediction errors at the higher level, so now I've closed it, but so the deviation between the variation expectation parameter and the prior expectation parameter, they increase. So whenever they talk about predictive processing and minimizing prediction errors, it's certain prediction errors which are minimized. It's not all prediction errors which are minimized, because of the prediction error between the prior and the variational distribution parameter would be minimized, then of course you would just always stay with a prior, and this is clearly not the idea. So, so prediction error minimization is not the whole story, or at least, or we can say there are more prediction errors than just the error between the data and the prediction. So this is how this then looks from a technical perspective. Of course, this is an example where this works nicely. So here these parameters can be inferred quickly. One can, however, also construct very simply examples where this whole thing doesn't work. So this was what it did here in the end, because it's always, if you look into the literature, it's always portrayed as like, this gracefully works and it makes a lot of sense and it's very nice results and so on. Yeah, if you want it to be, yes. If you don't want it to be, then you can also show that the whole thing doesn't work at all. So first thing, so one important thing that the whole thing works, so that actually the true but unknown cause is rightfully approximated by the variational expectation parameter, depends a lot, of course, on the relationship between the noise. So the data noise or the observation noise, as well as the prior uncertainty or prior tightness of the prior. So here are 3 examples where the whole free energy principle, it's still there, but it doesn't really work. So this is an example where the prior is very broad, so you don't see any isocontour of it. It's there, but it's very broad, and at the same time so the prior precision is very low. At the same time, the data precision is also very low. So you see that you have a hard time in the data identifying the bump, which is still at 1, so you don't see it. If you look at the free energy function, that as a function, of course, of the variational parameter that results from such data, you see that there are many bumps and valleys, and there's nothing like this where an algorithm now would easily go in. Yeah? So if there's, what this means, if there's a lot of noise, this whole thing doesn't work, if there's a lot of noise in the data. It's kind of clear, but this also shows what's going on. The same also doesn't work, and this is why there was this relatively tight prior previously. If the prior uncertainty is a little bit broader, here the noise level in the data is not the problem. The problem is that if one looks at the free energy function, the prior sits a little bit in a dip, and the algorithms don't really get the prior expectation parameter necessarily out here. Definitely not the algorithms that I tried. Of course, this is always where you can play around, use different algorithms, do width search, do whatever. These are typical problems in nonlinear optimization. Here you have a minimum of the negative free energy, because the data is quite clear, which translates itself into this clear maximum of the free energy or minimum of the negative free energy. However, the algorithms still don't get the expectation parameter really into that minimum. And finally, this is not really a problem, but it's more like a feature of the whole thing, but it shows also that kind of a boundary case where you would basically stay with your prior. If you have a very tight prior on where the cause is, you still have relatively good data, like in this case. You have this very strong well of the free energy, and there is a little bit of a additional well here. Maybe make this a little bit bigger. So there's a little bit of an additional well here where the true but unknown cause is, but again, because you're already in a well and the gradient, the gradient might already be 0 at this location, you also don't move out of this. So what I try to do with these figure 15.7 is to show that it's not as perfect as sometimes communicated. The thing is, of course, if you communicate that things are a little bit more complex, then people are like, I can't hear that. My brain is hurting already. Tell me something easy. Deep neural networks are great. Thanks. Now I'm feeling better. Yeah. But this is, of course, interesting. And if you want to do science on this and study free energy principle more, then, of course, these things are interesting. And, yeah. But, of course, the whole thing would be more interesting even if this would be put together with empirical data. So, good. So that was my little example of static perception of a bump under a blanket inspired by Horst and Kitty, my two cats, although one of them is a tomboy cat, Horst, obviously. Yeah, I think that's about it. Yeah. So, of course, much more could be said about variational inference, much more could be said about DCMs, but we have to stop at one point, and this is what we do now. Questions? No, I mean, you have the study questions, so go over them. They are, of course, meant to focus on the most important things and basically to help you memorize certain things. You have to also appreciate that this whole variational inference thing, this is really research-oriented teaching. In the sense that this is an active field of research, free energy principle is an active field of research. It's early days in the whole computational, cognitive neuroscience world. But then you're also supposed to learn recent stuff and not only stuff that is 100 years old. Good. If there are no questions, then we continue later with programming and continue next week with questions that you have regarding the study questions. And again, like last term, if there are no questions, next week I will leave. So because, yeah, nothing will happen. So it's really depending on that you have questions to clarify. Yeah? Good. Then let's have a break and continue at 10 or